Welcome to episode 39. Today's show is dedicated to the burning curiosity to know whether you and me are truly alone. The search for life on other worlds has always fascinated people from all walks of life. Currently, we have the Mars 2020 Mars rover mission by NASA's Mars Exploration Program. That includes the Perseverance rover, and the Ingenuity helicopter drone is due to land on Mars on the 18th of February 2021. Astronomers believe that there are hundreds of solar systems and thousands of planets, which mean that statistically the odds are favorable for finding another planet that supports life. So now let me welcome you all once again to our distinguished speakers. Today we have Romy Rodríguez. She's a PhD student in astronomy at the Ohio State University, and Professor Abel Méndez. Today we'll have a real Puerto Rican Planet Hunters show moderated by a real Puerto Rican, our beloved Kamille Morales. She's an artist science communicator, Caribbean Astronomy Society member, and Solar System Ambassador-JPL for NASA. So without further ado, I will hand over the mic to you.
Thanks for having me here again, and bienvenidos al Space for Women show. Y para mí es un placer. Today is my pleasure to present two of my fellow Puerto Rican colleagues and old friends I know for years. And it is my pleasure to present today Professor Abel Méndez and Romy Rodríguez. Professor Abel Méndez is a planetary astrobiologist and director of the Planetary Habitability Laboratory in the University of Puerto Rico in Arecibo. Professor Méndez is currently working on theoretical models of the suitability for life of planetary environments, the characterization and detection of potentially habitable exoplanets, and the observation of radio emissions of red dwarf stars from the Arecibo Observatory. Abel, siempre un placer. The floor is yours.
So thank you, Kamille. My pleasure to be here. So I will be talking today about habitable worlds from Arecibo, from our country of Puerto Rico, from our town of Arecibo. And I work at the University of Puerto Rico, which is nearby the Arecibo Observatory. So that's why I'm doing also research at the observatory as an astronomer, as a planetary scientist, as Kamille said. So let me start by showing you oceans in the solar system. Let's start by Earth. If you put all the water on our world in a droplet, it will be a small size. So even that some people say that our planet should be called ocean because it looks so blue instead of Earth. Actually, Earth is a better name. It's mostly composed of rocky environment. So Mars in the past probably had the oceans in the northern hemisphere. So about the same proportion of water. But if we look at moons in the Jupiter system, Europa and Ganymede, those moons have much more water per their size as Earth. Actually, for Europa, about more than 2 times the water. So these actually are water wars. The problem is that all that water is below an ice cap. So there is no surface water. And if we look farther away in the satellites of Saturn, Titan, and Enceladus, they have still much more water. So that's a normal thing that this water is, the point here is the water is abundant in the universe. So planets that are farther away tend to have more water, but the problem is that they will be too cold for that water to be liquid at the surface. So that water will be only liquid below the surface, below some deep ice. Then how to determine if a planet is potentially habitable for the astronomers? For the first thing, it has to have the right distance. As I said, if it's too far in the blue region here, then it will be too cold. Is this in the red region? And here at the center is the star, the yellow dot here. Then they will be too hot. So it has to be in between in this green zone. that we call the habitable zone. But it also have to have an atmosphere. So the moon is next to us. So the moon is actually in the habitable zone as Earth. But the point is that the moon is it doesn't have enough gravity to keep an atmosphere. So that's the first requirement, and habitable orbit, or the right orbit. You also have to have a habitable size, the right size. As I said, this is too small, then it won't have atmosphere, so it won't be able to hold some liquid. But is it too big, then it will have too much atmosphere. So water will be solid no matter the temperature due to pressure of the atmosphere. So Earth is about the right size. So habitable orbit, habitable size. So the other criteria, it has to have conditions similar to Earth. So some similarity to Earth, like having continents and ocean, that would be great. And I will explain that, why that is very important. So habitability is the suitability of an environment for life. We can simplify this problem by the classical elements. So you need for life, earth, water, earth, and fire. So when we say air, we mean a gas, you need an atmosphere, you need the water, a liquid, you need earth, solid. And why we need these three phases is because here below I show you the 5 more important elements for life. And you cannot find all these 5 elements in just one state. They won't be in the atmosphere, they won't be in the liquid region, they will be in the rock. They are mixed and in between all these phases. So this phase has to be in contact. And when I say fire, I mean some kind of energy like sunlight or chemical energy to support life. So if we put this together and try to see our planet, we see that the rainforests, they have abundant life is because they have the 4 ingredients in abundant quantities. That's why we have forests, because they feed on these elements. And those forests can support larger animals and then eventually intelligent life. But it's surprising that in our planet, which we consider so habitable, we have dry deserts, so dry that you cannot see even the plant. And the problem is here, the limiting factor is the water, precipitation. And we have a lot of water in the ice cap, but still the same problem. We don't see a forest of cold plants there. It's because water has to be liquid. In the clouds, we have lots of liquid water, but then the problem is the earth. You don't have that much soil that is transported as dust into the atmosphere. And the ocean surface, I should expect to be the ocean full of vegetation, for water plants everywhere, but it's not. It looks like a desert of life. And the limiting factor here is the same as the clouds, because the dust in the atmosphere precipitates when it lands in the ocean. So it can only feed much less organisms, and most of the life live next to the coastal regions because they can feed also in the soil there. And the deep ocean, it has 2 problems. It has the problem that there's not much atmosphere there as deeper you go. So there's not much oxygen, and there's also the sunlight, the energy. So it has a problem of energy. So that's the worst case scenario. So all these cases. The point here is that life on Earth that we know is so resilient and can be, in theory, adapt to everything. It was not able to adapt to be as abundant as in other environments as forests. So forests are the most habitable places on our planet. And the problem is to have a forest. Now you see that you need land, so you need the continents, but you need also precipitation to put water there. And for that, you have to have an ocean. So it's telling you that it doesn't work to have a planet just of land, a desert planet, or ocean planet. That's not good. You need something with land and ocean, something like Earth. If you want to have enough life and abundant life and food for complex animals and then intelligent life. So far we have detected about 50 what we consider potentially habitable planets, but I'm showing here just 24 of those are the best candidates. And for reference, here's Earth, Mars, Neptune, and Jupiter. And you see that most of these planets are a little bit larger than Earth because they're easy to detect, the larger ones. But the problem is that we don't know what type of planets are these. We can only see that they have the right orbit, as I said before, and they have the right size, but we don't know if they have the right atmosphere. And they could be tidally locked, always facing one side to the stars. So one side will be too hot and then the other side too cold and it will trap water, ice there. They could be desert planets. They could be ocean planets, or they could be Earth-like planets. So we don't know right now of all these 24 candidates, which one is good as Earth. At least they have maybe the right temperatures, but we need to have more details. So all these are only artistic representations because we don't know yet anything about their surface properties or even their atmosphere. So if we consider the solar neighborhood, the nearest star, we can estimate based on just pure statistics that maybe are over 100 planets potentially habitable near the sun. We don't know of each category, maybe we are the only one Earth-like, but at least potentially habitable in the solar neighborhood. But if you go farther away in the Milky Way, we might have up to 50 billion or much more if we consider the whole universe, 5 trillion. But we can forget about all the planets in our galaxy or farther away. We might be able to tell anything at all more than their size and their orbit for those that are nearby, just to recognize if these are planets just like Earth or just barely habitable. So future exploration of habitable worlds, today we only see the orbit and their size, and that's why we have to stress out that they are potentially habitable. We will know more about them in the next years, in this decade. We will know more about the atmosphere, and we will say, well, if we find water, oxygen, maybe they're likely habitable. Then in 20 years, we might have some indication of their surface properties, at least if they have ocean or land area. It's not because we are making the telescope look at the details of the surface, but as the planets rotate, we will see the light changing due to lighter areas and darker areas related to land and oceans. So we might have some idea if they have that. If they are all covered with clouds or desert or ocean, they will look the same. So there will not be any change in light. And in 30 years, maybe life. Just by looking at that life from that planet, we might tell that there is some wide abundant vegetation through the whole planet. So that's what we might expect in the next years. And that would be great. So Arecibo Observatory was a great telescope. And that's one of the instruments that we also use to understand the universe. And in general, it did research about the atmosphere. It did research about planetary science through the radar, looking at the surface of Venus and looking at asteroids, nearby asteroids. But it also do astronomy science, look at stars, galaxies, and the universe. And that's why we use the telescope for looking at stars with those potentially habitable planets, not to learn about the planets because those are hard to see in the radio spectrum yet, but just to understand how the star is so active that might damage any life on those planets. The Arecibo Observatory, we still use the Arecibo Observatory, even that the telescope is not anymore for us, but there's a lot of data, and I have 3 particular students, Kevin Ortiz, Genesis, and Ariana. These students are very active working with the before and now, using archaic data that we have a lot of things to study for years to come. So there's up to 50 years of data there that all astronomers are using everywhere. So that's great. And we have a lot of work to do. And I work with a lot of people, and I love to work with students. And that's something that we hope to do for many years to come. So thank you very much.
Thank you so much, Abel, for your insightful talk. And we'll be having questions in the second part of the show. So we'll be presenting Romy right now. And Romy is a Cuban-born Puerto Rican astronomer. She is currently pursuing a doctoral degree in astronomy at The Ohio State University, where she works under the supervision of Professor Scott Gowdy. She earned a bachelor's and a master's degree in physics from the University of Puerto Rico, Rio Piedras. Her work broadly involves the detection and characterization of extrasolar planets. Currently, she is investigating how to constrain the internal structure of small exoplanets by using precise measurements of their physical properties and that of their host stars. And without further ado, Romy.
Thank you, Kamille, for that introduction. So yes, I am a 4th year astronomy PhD student at Ohio State University. And today for this talk, I am gonna talk a little bit about the detection and characterization of exoplanets. So to give you a bit of background on my career first, so I grew up in this beautiful island of Puerto Rico, in Caguas specifically. And since I was little, I knew that I wanted to do astronomy, but unfortunately, there's no astronomy programs here in Puerto Rico. And so I decided to study physics. So I earned my bachelor's and master's degree in physics from the University of Puerto Rico, which you can see a picture here. And later I decided that I wanted to go to grad school because I wanted to learn more about exoplanets. And so I applied to graduate programs in the US, and I got accepted to the Ohio State University, where I've been a PhD student since 2017 there. So here's a picture of me with some of the faculty and graduate students. And so at OSU, I've been really lucky to work with a variety of faculty on a few different projects. And so this talk is going to be a sort of tour of a few of my projects there. But to give you a little bit of background, and I know Professor Abel already mentioned some of this, but so just to give you some definitions, exoplanets are basically planets that orbit stars other than the sun. And in the past 25 years or so, we have witnessed a true revolution in this field. As you can see here in this histogram showing the number of detections per year. And you can see the almost exponential growth in the past years, in part thanks to the Kepler Space Telescope. And one of the biggest discoveries and triumphs in this field has been the discovery that there are so many, the Milky Way galaxy is teeming with exoplanets. There are exoplanets everywhere. And moreover, they are actually really, really diverse. So here's a plot showing the mass and period distribution of exoplanets detected so far. They're color-coded by the detection method. And you can see the plot here is in log scale. It's not updated, but you can see that they span a really wide range in masses and periods, and that they actually don't look a lot like the planets in our solar system, some of which are plotted here for reference. So that they're very, very diverse. So I'm gonna jump right into my first project that I worked on at OSU, which was involved the search for stellar flares on M-dwarf stars. So first, flares are bursts of energy that happen on the surface of stars. The sun, for example, has flares and other magnetic phenomena. And M-dwarf stars are stars that are cooler and smaller than our own sun. And they're also everywhere. They're the most common type of star. We just can't see it because they emit most of their energy in a part of the spectrum that we can't see. But one of the motivations that we have for searching for flares on these types of stars is first because they're very, very active. Even though they're small, they're more active than the sun. And second, because going back to the topic of habitability that Professor Abel discussed, stellar flares are actually hypothesized to be very harmful for planets in nearby orbits to their stars because they emit a lot of energy, right? And if they happen very frequently enough, then they can erode the atmosphere of a potentially habitable planet. So for my project, we took a sample of 1,300 stars, M-dwarfs in the Northern Hemisphere, and using a simple statistical algorithm, we confirmed 62 stellar flares. And we went on to measure their flare energies. And the most interesting result I would say that we found is that the fraction of stars that flare increases with stellar type. So what does that mean? So here's a plot showing a histogram of the different types of stars. They're binned by their spectral type. So spectral type is basically a measure of how hot a star is. And going here from 0 to 5 the sequence gets cooler, right? So an M0 is hotter than an M1 is hotter than an M2, and so on. And if you take the fraction of stars that flare that are M0 and divide it by the total number of stars, then you get this distribution. And you can see that the cooler stars are flaring more. And so that's what we show here. Another project that I worked on, so I worked on the search for planets that we call hot Jupiters. So these are gas giant planets with periods of between 3 and 10 Earth days. And they, the discovery of the first exoplanet that we detected around a sun-like star was a hot Jupiter. And it really changed our view of the universe and of planet formation because we didn't expect planets to form so close to their host stars. And so it was a really huge discovery in our field. And at Ohio State University, I had the honor of being a member of the Celt Survey. So Celt was a ground-based transit survey that was looking for hot gas giants, mostly around hot A-type stars. And it stands for the Kilodegree Extremely Little Telescope, as you can see here. We had 2 observatories, one in the north and one in the south. We call it extremely little because it was actually very tiny. The aperture was only 42 millimeters. So it was very small. And my role in that collaboration was to validate and follow up the most promising targets. So basically I analyzed observations that were provided to us by our network of follow-up observers, and we decided whether this candidate was worth following up. The way that Celt searched for exoplanets was via the transit method. So basically, when a planet passes in front of its star, it blocks out a tiny fraction of light that we can measure as a dip on its light curve. And so basically, so you can see here, right, as the planet passes, it's blocking a little bit that we can measure. And so that is the most prolific type of method that we have today. We have uncovered thousands of exoplanets using this method. And that's how Celt searched for planets. So during my time, I had the privilege to work on lead the discovery of two really cool objects. So the first one we call Celt 25b. So this was a substellar companion orbiting a young and rapidly rotating A star. So an A star is basically very different from an M dwarf, right, that I discussed earlier. An A star is a star that is much hotter than the sun. And you can see here I listed some of the properties that we inferred for this system. And what I want you to notice is that the period of this planet is only 4.4 days. So a whole year on this planet is only, a few days. And moreover, the temperature of the star is very, very high, much higher than the sun, which means that because this planet is so close to the star and the star is so hot, when you estimate the temperature, it turns out that this planet is actually, about as hot as some of the coolest stars. So it has an equilibrium temperature of 2300 Kelvin. And then another cool object that we worked on was Celt 26b. This was an inflated hot Jupiter on a polar orbit around another A star. And so again, if you look at the period, it's actually even shorter. And the host stars are also very hot. So this is in the top 10 hottest planets, actually, that we've ever detected. And the results of this work were published last year, if you want to check that out. And then lately, what we've been working on is trying to understand some aspects of the individual planet properties of the planet and how they connect to its habitability. So one aspect that we've been interested in is the surface gravity, because it turns out that the surface gravity is linked to habitability in a few interesting ways. So first, it coupled with the temperature and the mean molecular weight of the atmosphere, it dictates the atmospheric scale height of a planet, or in other words, the thickness of the atmosphere, how thick the atmosphere is. And also, most importantly, perhaps, is that it could be one of the main drivers of plate tectonics. So we know that on Earth, plate tectonics are very important for habitability because it helps regulate surface carbon abundance, and it drives the formation of features like mountains, volcanoes, and it sculpts the topography of a planet. And so to the extent that the surface gravity causes plate tectonics, and to the extent that plate tectonics are important for habitability, then it's really important for us to be able to understand how we can measure the surface gravity. And so another thing we did was to explore the connection between the surface gravity and the core mass fraction of exoplanets, specifically terrestrial small exoplanets. So here is a plot showing the mass radius. So we considered the planet K2-290. And what this planet has already been characterized, but we took, this is showing the mass radius uncertainty ellipses for this planet. First, assuming that the mass and radius are not correlated, and so that's in red, and then assuming that that they are correlated via the additional constraint of surface gravity. And you can see that for the black ellipse, it's following the line of constant core mass fraction more closely than the red ellipses, than when you're not using this constraint. And so this basically tells us that the core mass fraction and the surface gravity are related. And if you know the surface gravity very well, then you can use that to constrain the core mass fraction of a terrestrial planet. So that was also published this year, if you want to check that out more. But basically, that's all I have, and thank you very much for your attention.
Thank you so much, Romy. Thank you for all this amazing information. So now we're going to start with some questions. So what is the current definition of habitability and how do we measure it?
Well, habitability is known as the suitability of an environment for life, how good an environment is for life. So this is measured or related how much resources like food are available for life. In terms of biology, this we call this like the productivity, how much biomass, how much mass related to life can be produced by unit of space and time. So that's how we measure habitability in practice.
And in the aspect of measuring it, I guess it will be a little bit more complex when we talk about microorganisms, and since we're seeing all this exoplanets from a distance and usually with the transit method, as Romy was saying. So what would be a little bit of the measurements that we could use realistically right now?
Well, we can measure habitability directly as Earth is our example for life. So we need to learn a lot more about different measurements, different environments, especially extreme environments, measure how life, especially microbial life, could be available, could be produced by unit of space and time. And I see that my face is in quantum state right now. And and that's that serves for understanding the potential of life in the solar system objects. But for exoplanets, those planets are on other stars, they're far away. We cannot tell anything at all about their surface yet. So we can only estimate what might be the general condition and the potential for a global biosphere, if any at all. So for right now, they're only estimates. Only we can do actually measurement of Earth and in the solar system.
So maybe Romy will help me with this one. What are the next missions studying habitability in other worlds?
Yeah, I can start and then Professor can chime in. So some of the upcoming missions that I'm personally excited about is the James Webb Space Telescope, which is scheduled to launch this year in October, fingers crossed. And so this is gonna be the next like big NASA mission. So it's gonna be like the NASA successor of the Hubble Space Telescope. And basically it's gonna have really, really sensitive spectrographs in the near infrared that are going to be are going to sniff the atmospheres of the best planets that we identify as the best planets to potentially have life as we know it. And so that's one exciting mission. And then and if my advisor saw this talk, he would kill me if I didn't mention this one. But there's also HABEX. It's a mission concept for a coronagraph that's gonna directly image the first Earth-like planets around sun-like stars. So we're looking forward to that, but it's still very early stages. And then Professor, if you want to mention others.
I will.
Well,
Yeah.
I just want to mention in general that we are moving from detecting planets. That's what we have done in the last 20 years. And now moving to characterizing, to understanding these planets. So as Romy said, these missions are focuses in biosignature detections of indicators for life. And that's the next step.
I think we are living in exciting times because a couple of years ago, 20 years ago, Carl Sagan was talking about these planets that we will find. And now we have so many thousands of planets that we're finding now. And now we're able to start characterization. So I think we are living in very exciting times. And I will also like to add some other missions like Europa Clipper mission, which is another really cool mission that will be studying the one of the biggest moons of Jupiter, which we hypothesize that there's an ocean under the ice. and that is a very exciting topic. And this mission will be a flyby. It will be doing close flybys to kind of like take measurements and do some collect data in each flyby for a long period of time, so we can actually know and confirm if there is an ocean and how deep it is, and then measure the salinity of it and so many other things without even being there. So I think that will take us one step further in studying these icy worlds, which we have a couple of them so close by, close astronomical terms. So that is a very exciting mission to be looking forward to. And the closest one, like Kian mentioned, which is the Perseverance rover. So I hope you guys are paying attention, because in February 18, very close, we'll be having our own astrobiologist in Mars, taking samples for probably a future mission to take sample return to Earth. And we'll have our first helicopter in another planet. So these are very exciting times to study habitability. And to continue with another question, this one is mostly for Abel. What does the future of the Arecibo Observatory look like? And will it have more capabilities, especially for exoplanets?
Well, that's a very interesting question, because, building a new telescope, that will be something expensive, hard. It will take some time. But we were working since December of new plans of the observatory and new ideas. And the final document just came out this week for the general public to support. And when we finally decided the specification, I was totally amazed. So in the 60s, when this telescope was built, it was a dream telescope. It was something out of science fiction. Now it looks like that. Now we are in the 2020s. That's amazing telescope that we are planning. So it will have a lot more capabilities, not only as before to study atmosphere, to study asteroid, more powerful radar also, but also many things to study exoplanets. It will be a much as sensitive as the one in China. It will use a lot of technology, different technology. It's a state of the art. This is something amazing that we are planning to build.
Well, that is very exciting news, because I don't know if some people in the audience know about, but our Arecibo Observatory collapsed in December last year. And it's been really hard for us that we love the science that we made in the Arecibo Observatory and what it meant to Puerto Rico. And we don't want to give up. So we want to rebuild, and even better, just like Abel said, so we can do even more science and inspire future generations to do more science and get a career in this field. And I have one last question on the preset questions, and then we'll pass for the chat ones. So when will be the soonest we may find extraterrestrial life?
I could say that we're looking for extraterrestrial life starting from Earth. And how on Earth? Because meteorites. People are looking for meteorites from space, trying to search if there's any microbial life. And even in the 1996, we have a potential Mars meteorite with life, but now we know that was a false call. It's very hard, but people still doing that. But otherwise, there's the solar system. So planets like Mars or future missions, like Kamille was telling about Europa Clipper. So there's the potential in exoplanets, looking at these atmospheres and looking at some gases that tells you that there is some life process going on this planet. So all these approaches, looking on Earth, looking in the solar system, looking in extrasolar planets, are competing, and scientists are competing. Who will be the first to detect life? And I know it's even very hard. And probably, and this is not in my best interest, because I do science about exoplanet. Maybe it's in the solar system, because we will have samples. Once we are able to eventually get in this decade the sample for Mars, not probably the rover doing there and finding life, because there will be many doubts. We need this sample back on Earth to study for a long time. That's the only way to say for sure we detect life. So probably Mars, if anybody at all, will be the first one to tell is there extraterrestrial life, for sure. Then we will have announcements and exoplanets that we detect indications for life, but I know there will be a lot of controversy on how we interpret those signals and what they mean, and many things that could go wrong in those interpretations. So that will be no final conclusion, but there will be many announcements, I hope so.
Oh, it's such a competition right now. Definitely. It's the new race. Finding life in another world is a very exciting time, definitely. And now we're going to start answering some of the questions from the public.
Martina, she is asking Professor Abel to talk more about the future exploration and the expectations over the next 30 years. Could you elaborate on that?
Well, the final thing that we might be able to do in 20, 30 years is looking at these planets that, in the best case scenario, we see only a dot of light. And only we are able to do that for the bigger, harder ones, where they can emit light. But we are interested to see that individual planets, rocky planets, as a dot of light. And we will analyze that light. Maybe we will sample the atmosphere and tell, well, we see that there's water there, we see oxygen, we see a methane. So gases that are necessary for life and are produced by life. So there is a combination, those three components are important for life. But we will also see that might be not enough, but looking at the light of the planet as the planet rotates, we see that it changes, telling you that there is a dark regions like oceans, which are darker than land areas. We will see some changes due to clouds. And we will tell, wow, that this planet have water, oxygen, methane. It has continents, it has oceans. And that will be probably the definitely point that then we will see in the atmosphere, we might be able to tell chlorophyll, some indication that there is a wide scale vegetation on the planet. And from that point on, we will say, okay, definitely, this is not only a potentially habitable planet. This is not only a habitable planet. This is a planet is inhabit. It has already life, but we won't be able to tell what kind of life. At least is that it has forests. That's as far, but we won't be able to tell at that point is it has animal or intelligent life, because we know the evolution of Earth. We having forests, and there was no animals at that point. They evolved later on, and that's at least we will know that it has vegetation. That's the point that in the 20 or 30 years we might reach.
Thank you, Professor Abel. Romy, would you like to elaborate on?
Yeah, I just wanted to add that that I think at the end of the day it's also going to take luck. Like we just have to get lucky and look at the right, position in the sky. Like, and we're only going to be able to do this detailed analysis of the atmosphere of planets on the nearest planets also. So unfortunately, we don't have access to the whole galaxy, but hopefully there's something nearby, and that is detectable also, right? Because the galaxy could be rife with life, but if we can't detect it, then it might as well not exist at all. So
thank you, Romy. Jane Steen is asking, what about more than atomic models, deeper than the matter to find life as frequencies based beings? Jensen, maybe you want to put the mic on and ask.
Yeah, my question is, in order to find life in other planets, what is life? So it's not based only on the 4 elements. For me, it's based on 5.
So Professor Abel, want to take that? Who wants to take that?
Oh, that question in particular is definitely right for Romy. So please, Romy, I need enlightenment here.
I mean, it's a very interesting theory, and I don't think I have enough knowledge to answer the question, but I will say that, I mean, you're definitely right in that we can only search for right now what we know, right? And I was talking to Kamille about this yesterday. Actually, we were talking about how we can't even define life on Earth. We have a very limited idea of it, and so, but the best we can do right now is to look for what we know, and that's why the field of astrobiology has a very Earth-centric view of searching for life, because Earth is all we know, and animals and humans are all we know. So we're trying our best to find that first, if we can, and in many years then maybe we can find more extraordinary things, but it will take better technology and better instruments.
Thank you, Romy. Chris from LinkedIn, he's asking, can we ask about space-based VLT far beyond JWST, or a lunar counterpart to Arecibo being discussed for the dark side? Professor Abel.
Yes, okay. The VLT, Very Large Telescope, there are many big, huge telescope plans, and even considering putting a telescopes on the moon, especially a radio telescope in the far side, because it will be block all the radiation from Earth, which is very hard. So we had a lot of work using Arecibo Observatory with all this terrestrial interference, and putting a telescope in space, it just take away the interference of the atmosphere. Making telescope putting telescope on the moon, we also block radio plus all the interference of the atmosphere. So we have a very bright future of telescope, but it's not only these telescopes to have to be big, but also to work as a network, as an array of telescopes. That's the big deal of your constructing telescope, because that not only the size increase the sensitivity, so, and that's good, but you also need spatial resolution, details. So you see the things very far, but if you see that thing that is very far and it look blurry, that's not good. So then you make an array of these big telescopes, and then you will have a clear picture. So we definitely planning many telescopes for the future.
Thank you, Professor Abel. There is another question from Jody. Life would contain the so-called CHNOPS molecules, question mark, or would it embrace other carbon-based forms? Any discovery so far that could lead us to a preliminary conclusion? Romy?
I mean, Professor can chime in here. I think that as far as exotic life forms on Earth, we do know of the existence of extremophiles. We know of organisms like tardigrades and so on that are actually very resistant to well, what we consider very harsh conditions, unhabitable conditions. So we know they have different categories, but there are things that can survive in sulfuric or very acid lakes, things like that, or very acidic environments, or very environments with high concentrations of salt, or in very low temperatures at the bottom of the ocean, things like that. So it's very likely that if we can find those things surviving here on Earth, that they exist in other planets. But it'll be very hard to obtain a reliable, like a confirmation of life, for sure.
Thank you, Romy. Professor Abel, would you like to comment here?
No, that's fine. She answered everything.
I would like to add to that. We were talking about the life forms that we know now, and that's what we are looking for. And there are other missions that are being planned, like, for example, to go to Titan, which they have liquid methane. And we don't know if there's any life form that could survive and live in that environment in liquid methane, because we know methane here in gas form. And we have some creatures here under the ocean that live off methane as an energy source, but we don't know how will it thrive or something in an environment like Titan, for example. So maybe that will be the closest thing, the closest place we could start looking for a different type of life. Maybe it evolved in a different type of way, but it's like Romy said, we are starting from where we know what we know, and we still don't know a lot of our lives here on Earth, including the tardigrades, for example. And just if you didn't know, but the tardigrades have been taken to space, and some of them have survived. So that puts them in a very resilient list of possibilities and of life forms that we may find or we might look for in other planets and other bodies. So it all stems from starting to study here on Earth and then stepping forward to the next step, to the next worlds. And I also wanted to add, Abel, I don't know if you wanted to comment quickly on that strange signal that you detected from the Arecibo Observatory that was featured on the One Strange Rock in the National Geographic show.
Wow.
It was a little bit controversial, yeah.
Yeah, okay. In 2017, we have a big deal because the National Geographic was filming a documentary, One Strange Rock. It was, I think, July 2017. So previous to Hurricane Maria in September. So, and we haven't seen, and they asked me just to be natural, and so I was supposed to talk with another colleague, Edgar Rivera, from the observatory. Now he works at the LPI. And I said to Edgar, I was planning to ask you anyway something today, so let's do it live for the cameras and for real, just answer for real. So my question was about a strange signal that I was getting, so probably some interference or something. So I asked that, and he said, that's weird in camera. So all the production was like, oh, wait, what are we having here? Aliens? And the rest is history. That filters out in the media, and people were asking us if we detected. That's a normal thing. Like looking in the radio spectrum, you see a lot of weird stuff. But that weird stuff is usually interference from Earth or satellites. That's something common. And sometimes you can definitely say, okay, this is terrestrial thing. This is astronomical. But sometimes you don't know if either of those two. But it doesn't mean no aliens. It doesn't mean aliens. It just means that you don't know at that moment. So we eventually do observation, and we discovered it was a weird signal, but caused by different satellites simultaneously, and the geometry of the observatory. So it was something not common, but we were able to figure out what was going on. So that's the story.
Thank you so much, Professor Abel. Thank you, Romy, and thank you, Kamille, and thank you everyone for your insightful and active participation. I'd like to also have a mention, and on the 11th of February, right, there is the International Science Day, and UNOSA is organizing a public event for you all to join the UNOSA Space for Women network. So you will have to register, I believe. Go on the Space for Women UNOSA webpage, and you will learn about more other mentors initiatives. And I'd like to invite you also to next week's show, episode 40. It's about space architecture and design, future approach to human experience. So thank you so much for hanging out this weekend. It was an amazing episode, and stay well and safe, everyone. Thank you so much.